The sound arrives before the machine becomes visible. A deep metallic grinding, a rhythmic clanking, steel scraping through gravel under hundreds of tons of weight. Then the structure appears through the morning fog above the river. A floating industrial platform the length of a small building, wooden hull, steel frame rising 3 stories high. A rotating ladder stretching forward into the water like the arm of some mechanical creature. At its end, a chain of iron buckets, each bucket roughly the size of a bathtub, each one capable of lifting nearly half a ton of sediment in a single scoop. The chain never stops moving. Bucket after bucket descends into the riverbed, cuts into mud, gravel, and stone, then climbs upward, dripping with wet earth. Inside the dredge, the noise becomes overwhelming. Steam engines thump against thick iron pistons. Boilers push hot vapor through pipes that rattle constantly under pressure. Belts spin. Gears grind. Steel rollers scream as tons of material move across vibrating screens. Workers shout to each other over the noise. Most of them cannot hear their own voices. The entire machine weighs close to 500 tons. And yet it floats, slowly crawling across rivers and floodplains, eating the ground beneath the water. Hour after hour, day after day. This was the bucket line gold dredge, one of the most powerful extraction machines of the early 20th century. In the popular story of industrial progress, machines like this appear almost as inevitable milestones. Gold had always been trapped in river sediments, hidden in gravel and mud. Before dredges, miners had to dig manually. Shovels, pans, small sluice boxes. A slow and uncertain process. But the dredge changed everything. A single machine could process thousands of cubic meters of riverbed every day. Entire landscapes could be turned over in months. Where small groups of miners once struggled for a few ounces of gold, now massive mechanical systems could extract it at industrial scale. In textbooks and documentaries, this moment usually appears simple. Human ingenuity solved a problem. Machines increased productivity. Resources became accessible. Economies expanded. The dredge becomes another example in a long sequence. Steam engines, steel mills, railroads, hydroelectric dams, technology advancing step by step toward modern prosperity. Museums often display photographs of these dredges resting beside rivers, huge wooden structures towering above the water. Visitors stand beside them and imagine the awe of early industrial engineering. Labels usually emphasize the same points: innovation, efficiency, productivity. The dredge is presented as proof that technology could transform nature itself. Rivers could be reorganized, land could be reshaped, hidden resources could finally be recovered. In many ways, the dredge fits perfectly into the familiar narrative of progress. A problem existed. Engineers designed a machine. Productivity increased. The economy benefited. The story feels orderly, even elegant. But when historians and engineers begin examining the surviving technical documents more closely, the picture becomes slightly less clear, not dramatically different, just harder to reconcile with the simplicity of the story. Because the same records that describe the dredge's impressive output also contain details that rarely appear in popular accounts. Details about noise levels inside the machinery room. Details about mechanical failures. Details about working conditions during continuous 24-hour dredging cycles. None of these details necessarily contradict the idea of technological progress, but they introduce a question that is rarely asked. If machines like the 500-ton gold dredge represented such an obvious step forward in industrial development, why do some of the most concrete details of their operation almost never appear in the familiar story? And why do they appear so frequently in the original documents? When engineers describe the bucket line dredge in technical reports, they often began with numbers, not with progress, not with innovation, with measurements. A typical large dredge from the early 1900s processed 2,000 to 4,000 cubic meters of river sediment per day. The bucket chain alone could carry 70 to 100 steel buckets. Each bucket might weigh 350 kilograms empty, and far more when filled with wet gravel. The chain moved continuously over massive rollers. One full cycle could take only 2 to 3 minutes. That meant the riverbed was being cut and lifted almost constantly. Inside the hull, the dredge functioned like a moving factory. The buckets dumped their load into a rotating steel cylinder called the trommel. The trommel could be 10 meters long and 2 meters in diameter. It rotated slowly while water sprayed through pipes at high pressure. The purpose was simple: break apart the gravel, separate the fine sediment, allow heavier particles, including gold, to settle into sluice boxes lined with metal riffles. Everything else continued down the system. Rocks, sand, mud, all of it eventually left the machine through a conveyor system and dropped behind the dredge in long piles. The dredge literally rebuilt the landscape as it moved. In photographs taken after dredging operations, the river valley often looked completely transformed. Instead of natural riverbanks, there were long rows of tailing piles, gray ridges of stone stretching across entire floodplains. In the narrative of progress, this transformation is often described as efficiency. The machine allowed miners to process land that would otherwise remain untouched. But when we look at engineering documents and operating logs, a different set of details begins to appear. The first concerns continuous operation. Many dredges ran 24 hours a day. Stopping the bucket chain was expensive. Steam pressure had to be stabilized again. Mechanical alignment could shift. Production targets would fall behind. So operators preferred to keep the machine moving. This required multiple work shifts, typically 3 crews rotating through the day and night. Inside the dredge, the environment could be difficult. Boilers generated intense heat. The temperature near the engine room sometimes exceeded 40 degrees Celsius. Steam condensed on metal surfaces. Oil mixed with wet sediment underfoot. Workers moved carefully along narrow steel walkways, while the entire machine vibrated constantly. Noise was another factor. Bucket chains slamming against rollers, steam pistons striking rhythmically inside cylinders, gravel crashing into the trommel drum. Contemporary observers sometimes described the sound as continuous thunder within a wooden hull. Communication between workers often required hand signals. Verbal instructions were difficult to hear above the machinery. Then there were the mechanical stresses. A dredge lifting thousands of tons of sediment every day experienced enormous strain. Bucket chains could stretch. Links sometimes cracked. If a bucket chain broke while operating, hundreds of kilograms of steel could fall violently inside the ladder structure. Repair crews had to climb along the frame to remove damaged components, sometimes above moving water, sometimes in darkness. Engineers knew these risks. Maintenance logs from several dredging companies describe frequent repairs. Bearings overheating, gear teeth wearing down, bucket edges cracking after striking large rocks. In some cases, operations paused for hours while crews replaced broken steel parts weighing hundreds of kilograms. None of this was hidden information. It appeared clearly in operating manuals and engineering journals. But these details rarely appear in the simplified narrative of the dredge as a symbol of industrial efficiency. Another detail also appears in the documents, one that receives even less attention. Gold recovery rates were not always as high as popular accounts suggest. Early dredges sometimes recovered only 60 to 75% of the gold in processed sediment. The rest remained trapped in fine particles washed away with the tailings. Engineers experimented with different riffle designs and sluice configurations to improve recovery. But perfect efficiency was impossible. Some gold simply passed through the system. Yet the dredge continued operating because of its sheer scale. Even partial recovery could be profitable when thousands of tons of sediment were processed daily. This raises an interesting question. If the dredge represented such a clear improvement over earlier mining methods, why do the technical documents describe so many compromises? Mechanical stress, frequent maintenance, incomplete gold recovery, harsh working conditions. None of these details invalidate the importance of the machine, but they complicate the clean story we usually hear. The story in which the dredge appears as a smooth and inevitable step toward modern industrial mining. When the original records are examined more closely, something else begins to emerge. Not a contradiction, but a sense that the historical narrative may have simplified far more than we usually notice. Because once these details start appearing in the documents, they begin to raise a different kind of question. Why do they appear so frequently in engineering records? and so rarely in the story most people learn about these machines. By the time the bucket line gold dredge became a familiar image in mining regions, a certain interpretation of the machine had already taken shape. The dredge was presented as the logical next step in mining technology, a mechanical solution to the limitations of manual labor. Where miners with shovels could move a few cubic meters of gravel in a day, the dredge could move thousands. The comparison felt overwhelming, and for that reason, the machine quickly became an icon of industrial efficiency. But when historians compare this popular narrative with the technical literature of the same period, an interesting gap begins to appear. Not a dramatic contradiction, more a pattern of simplifications. Some details emphasized repeatedly, other details quietly disappearing from the story. The first simplification concerns the idea of mechanization replacing labor. In many museum explanations and historical summaries, dredges are often described as machines that reduce the need for miners. A single dredge could supposedly perform the work of hundreds of individuals. And in one sense, this was true. A dredge crew might consist of 15 to 25 workers per shift, depending on the size of the operation. Compared to earlier placer mining camps, the number of workers physically digging the ground was indeed lower. But the technical records suggest that the story was not simply about replacing labor. It was about reorganizing it, because although the dredge automated the lifting of sediment, it created new forms of work that had not existed before. Mechanics had to monitor steam engines running at constant load. Lubrication crews regularly applied oil to dozens of rotating bearings. Boiler operators maintained water levels and steam pressure throughout the day. Electricians appeared later, once many dredges converted from steam to electric motors. And then there were the repair crews. These workers dealt with the parts of the machine that wore down fastest. Bucket edges grinding against gravel, chain links stretching under repeated loads, rollers carrying several tons of moving steel every minute. In some dredging operations, maintenance became such a constant task that additional crews worked exclusively on repairs. The dredge did not eliminate labor. It redistributed it into more specialized forms. But this distinction rarely appears in simplified narratives. The second simplification concerns the pace of mechanization. When people look back at the early 20th century, it is tempting to imagine dredges quickly replacing earlier mining methods. But historical records suggest that the transition was much slower. Many placer mining districts continued using manual or semi-mechanized techniques well into the 20th century. Dredges required large capital investments. Building a single bucket line dredge could cost the equivalent of millions of modern dollars. The hull had to be constructed from heavy timber or steel. Massive boilers or electric motors had to be installed. And most importantly, the operation required sufficient deposits of gold-bearing sediment to justify the expense. For that reason, dredges only appeared in certain locations. Large floodplains, ancient river channels, wide valleys where thousands of tons of gravel could be processed continuously. In smaller deposits, traditional mining methods remained more practical. Yet in many historical summaries, the dredge appears as if it quickly dominated placer mining everywhere. The slower and uneven adoption of the technology becomes less visible. Another exaggeration appears in the way dredges are sometimes described as machines that liberated workers from dangerous labor. Compared to underground mining, placer dredging did remove certain risks. Workers were not exposed to cave-ins inside deep shafts. They were not drilling into rock faces with explosives. But this does not mean the dredge environment was free of hazards. Contemporary accident reports describe several recurring problems. Bucket chains occasionally jammed when large rocks entered the system. If operators tried to restart the chain too quickly, the tension in the links could snap. Steel components weighing hundreds of kilograms could suddenly break loose. Another hazard involved the dredge ladder itself. The long steel structure that carried the bucket chain into the riverbed sometimes required manual inspection. Workers climbed along narrow beams above moving water while the chain rotated nearby. Even a momentary slip could be dangerous. And then there were the boilers. Steam dredges operated under high pressure. A poorly maintained boiler could release superheated steam into the engine room. While catastrophic boiler explosions were rare, smaller failures did occur. These incidents were recorded in technical reports and company correspondence. But again, They rarely appear in the simplified story of dredges as purely progressive machines. The third omission concerns something even more subtle: the scale of environmental transformation. When dredges moved through a valley, they did not simply extract gold. They reorganized the entire landscape. Each day, thousands of tons of sediment passed through the machine. After gold was removed, the remaining gravel exited through conveyor belts and stacked behind the dredge. Over time, these piles formed long ridges known as tailings. In some regions, these ridges stretched for kilometers. Natural river channels disappeared. Wetlands were drained or redirected. Floodplains became fields of loose stone. This transformation was not hidden. Photographs from dredging districts show landscapes completely reshaped by the machine. Yet in many retellings, this change is described only briefly, often framed as an unavoidable side effect of progress. The emphasis remains on the gold recovered, not the terrain rearranged. What becomes interesting is how consistent these patterns are across different sources. Popular narratives emphasize productivity. Technical documents describe maintenance, limitations, and environmental impact. Neither source is necessarily incorrect, but they are clearly focusing on different aspects of the same machine. The result is a subtle shift in perception. If someone only reads simplified historical accounts, the dredge appears almost perfectly aligned with the idea of industrial progress, a machine that solved problems and unlocked resources. But if someone spends time with engineering reports, company records, and field studies from the same period, a more complicated picture emerges. The dredge still represents a remarkable piece of engineering, but it also appears as part of a much messier industrial reality. Constant mechanical stress, large financial risks, difficult working environments, and landscapes permanently altered by the scale of extraction. None of this necessarily disproves the idea that dredges contributed to economic growth, but it does raise a question about the story itself. Why did the simplified version become so dominant? Why did certain aspects of the dredge become symbols of progress, while other aspects remained largely confined to technical archives? To understand that, we need to look at something slightly different, not just the machine itself, but the broader narrative surrounding industrial technology during that period. Because the story of the dredge did not exist in isolation. It appeared at a time when machines had already begun to represent something larger than their mechanical function, something symbolic, and that symbolic role may help explain why the story was told in a particular way. By the early 20th century, machines had begun to represent more than mechanical tools. They had become symbols, symbols of national strength, symbols of modernity, symbols of economic transformation. Across industrializing countries, enormous machines were increasingly displayed as evidence of progress. Steel mills, hydroelectric dams, ocean liners, railway locomotives, and in mining regions, the bucket line dredge joined this visual language of industrial achievement, standing 3 or 4 stories tall above the water. With its steel bucket chain constantly climbing out of the riverbed, the dredge made a powerful impression. Visitors described the site as both mechanical and monumental, a moving factory floating on a river. And this visual power mattered, because by the early 1900s, governments, companies, and industrial investors all had reasons to promote a particular interpretation of technology, not through conspiracy, but through alignment of interests. The dredge represented something useful for each of them. For mining companies, the machine symbolized efficiency and scale. A dredge costing hundreds of thousands of dollars required substantial investment. Investors needed reassurance that the technology represented the future of extraction. Promotional materials from dredging companies often highlighted impressive statistics, daily production figures, total gold recovered, length of river valley processed. Photographs frequently showed the dredge from low angles, emphasizing its massive structure rising above the water. Sometimes small groups of workers stood on nearby banks. Their size compared to the machine reinforced the message. Human labor had been amplified by industrial engineering. The scale of the machine became part of the marketing. For regional governments, dredging projects also carried political value. Gold mining had historically attracted waves of migration and speculation, but dredges introduced something different: large industrial infrastructure, permanent operations, corporate investment. Instead of temporary mining camps appearing and disappearing across rivers, dredging companies established longer-term facilities, workshops, housing areas for employees, supply networks connected to railways. This allowed local authorities to present dredging districts as signs of stable industrial development. Reports often emphasized employment numbers, the presence of modern machinery, the contribution of gold production to regional economies. The dredge thus became part of a broader narrative. Industrial modernization replacing frontier-style mining, technology bringing order to landscapes previously associated with chaotic gold rushes. Even national identity occasionally entered the picture. In several countries, large mining machines were presented as proof that domestic engineering had reached world-class capability. Technical journals proudly described new dredges with precise specifications. Bucket capacities, horsepower ratings, steel ladder lengths reaching 50 meters or more into the riverbed. Articles sometimes compared machines across countries. Which company built the largest dredge? Which operation processed the most gravel per day? Which mining district produced the highest gold output using mechanized dredging? This competitive framing encouraged a particular interpretation. Machines became milestones. Each larger, faster, more productive system symbolized progress. The dredge therefore functioned on multiple levels. It was an extraction machine, but it was also a public image of technological advancement. And once machines begin functioning as symbols, narratives around them tend to become simplified. Complex details fade into the background. Maintenance difficulties, partial recovery rates, environmental transformation. These aspects remain in technical records, but they do not fit easily into symbolic stories about progress. The simplified narrative does not necessarily arise from deception. Often it emerges from selection. Certain facts are repeated more often, others are treated as secondary. For example, promotional articles about dredging frequently highlighted production capacity. A dredge capable of processing 3,000 cubic meters of gravel per day sounded impressive, but the same articles rarely explained how often the bucket chain required replacement, or how many hours per month the machine stopped for maintenance. Similarly, photographs of dredging districts often focused on the machine itself, the towering structure, the bucket ladder cutting into the water, the long conveyor dropping gravel behind the hull. These images captured technological power, but they rarely showed the downstream effects of dredging across entire floodplains. Tailings ridges stretching across valleys, altered river channels, sediment flows changing the shape of wetlands. Again, this was not hidden information. Geological surveys and environmental reports sometimes documented these changes in detail, but those documents circulated mainly among specialists. They were rarely part of the public narrative surrounding the dredge. Another factor influenced how the story developed. Industrial technology during this period was often framed as part of a broader historical movement, a movement toward greater productivity, greater control over natural resources, greater economic growth. Machines like the dredge fit neatly into that storyline. They provided clear visual proof that human engineering could reshape landscapes and extract hidden resources. And once the dredge was placed into that larger narrative, the details of its operation became less central to the story. What mattered most was the symbol, a massive mechanical system transforming rivers into sources of wealth. This does not mean the narrative was false. Gold dredges did increase production. They did make certain deposits economically viable. They did contribute to mining economies in several regions. But the symbolic role of the machine also encouraged a simplified interpretation, a story where machines represented forward motion, where complexity was reduced to clear milestones of progress, and where the more ambiguous aspects of industrial systems quietly receded into technical documentation. This brings us back to the historical records themselves, because despite the simplified narrative, engineers, inspectors, and workers continued to produce detailed reports about dredging operations. Thousands of pages describing exactly how these machines functioned, how they broke, how they were repaired, how they reshaped landscapes over time. These documents never disappeared. They remained in archives, engineering journals, and company files. The interesting question is not why they exist. It is why they were so rarely integrated into the broader historical story of the dredge, and what happens when we begin to read them again today. If we step away from the simplified narrative and return to the documents themselves, the dredge begins to look slightly different, not less impressive, but more technical, more mechanical, and far more dependent on constant management than the symbolic story usually suggests. Engineering reports from dredging companies often read less like celebrations of progress and more like operational diaries. Page after page describes adjustments, small failures, routine interventions required to keep the machine moving. One recurring topic is bucket wear. Each bucket at the end of the dredge ladder cut directly into gravel beds that often contained quartz, basalt fragments, and compacted river stones. These materials were abrasive. After weeks of continuous operation, the steel lips of the buckets began to dull. Once the edge wore down, the bucket lost its ability to dig efficiently into the riverbed. Instead of cutting cleanly through sediment, it pushed material aside. Productivity dropped. Maintenance teams had to remove the bucket and weld or replace the cutting edge. Considering that a dredge might carry 80 to 100 buckets, even small wear rates meant constant repair cycles. Another frequently documented issue involved the bucket chain tension. The chain supporting the buckets could weigh several tons. When fully loaded with wet sediment, the stress on the ladder structure increased significantly. Engineers monitored the tension carefully. If the chain became too loose, it risked jumping off the guide rollers. If it became too tight, individual links could fracture under strain. A broken chain link did not simply stop the machine. It could send heavy steel components swinging violently inside the ladder frame. Repair crews sometimes needed hours to safely remove damaged links and reconnect the chain. Meanwhile, the dredge sat idle. Production targets slipped further behind schedule. Company records often describe these moments in neutral technical language. Chain tension adjusted after link deformation. Bucket assembly replaced following impact with large rock. But behind those brief phrases were hours of physical labor carried out by workers standing on narrow steel platforms above the water. Another set of documents focuses on gold recovery efficiency. Despite the massive scale of dredging operations, capturing fine gold particles remained a persistent challenge. The sluice boxes inside the dredge were lined with metal riffles designed to trap heavy minerals. But river sediment varied widely. Some gold particles were extremely fine, almost dust-like. Water flow through the sluice system could carry these particles away before they settled. Several mining engineers attempted to solve this problem by modifying the internal layout of the dredge. They adjusted water pressure, added additional riffle sections, installed mercury-coated plates to capture fine particles. Even with these modifications, recovery rates often remained imperfect. Some reports estimate that 10 to 30% of gold present in processed sediment escaped into the tailings. From a modern perspective, this might seem surprising. But at the scale of dredging operations, partial recovery was still profitable. The dredge compensated for inefficiency through sheer volume. Processing thousands of tons of sediment daily meant that even imperfect systems could produce substantial amounts of gold. Then there are the labor records, shift schedules, maintenance logs, worker assignments. These documents reveal the rhythms of life around the dredge. Many machines operated continuously, 3 rotating shifts, workers entering the hull at midnight, others leaving at sunrise. Inside the machinery spaces, heat from boilers mixed with moisture rising from wet sediment. Oil lamps or early electric lighting illuminated narrow corridors between rotating shafts. The smell of lubricating grease mixed with river mud. Operators monitored gauges measuring steam pressure and engine speed. Small adjustments were constant. Too much pressure could strain the pistons. Too little and the bucket chain slowed. Either way, production declined. Even the movement of the dredge itself required careful control. Unlike stationary factories, the dredge slowly advanced across the river valley. Steel cables anchored the machine to posts on the riverbank. By tightening one cable and loosening another, operators gradually shifted the dredge sideways. The bucket ladder carved a new section of riverbed. Then the process repeated, meter by meter, day after day. From above, the pattern of movement became visible in aerial surveys. Long curved rows of tailing piles tracing the path of the machine. Entire sections of valley floor rearranged by mechanical excavation. Geological surveys conducted decades later sometimes mapped these tailing fields, noting how natural river channels had shifted after dredging operations ended. Again, these observations were not secret. They appeared in government geological bulletins and environmental studies, but they rarely became central elements in the story told about dredges. The emphasis remained on production numbers, gold recovered, economic impact. What the documents suggest is something slightly different. The dredge was not simply a symbol of industrial power. It was a complex mechanical ecosystem. Engines, chains, boilers, sluices, cables, pumps, all operating simultaneously, all requiring constant attention, and all embedded within landscapes that changed as the machine moved. None of these details invalidate the idea that dredges contributed to mining economies, but they show that the machine's history was never as simple as the symbolic narrative suggests. All of this information existed from the beginning. Maintenance reports, engineering journals, government surveys, worker accounts. The data was always available. What rarely happened was bringing these details together into the broader historical story of the dredge, which leads to the final question. If we temporarily remove the familiar narrative of technological progress, what remains of the machine itself? If we set aside the familiar story for a moment, the dredge does not disappear. The machine remains exactly where it always was, a floating structure weighing hundreds of tons, steel buckets moving endlessly along a ladder, engines turning, sediment flowing through vibrating screens and sluice boxes, gold slowly separating from gravel. Nothing about the machine itself changes. The engineering remains real. The technical achievement remains significant. Designing a system capable of lifting thousands of tons of riverbed material every day required remarkable mechanical coordination. Chains, gears, pumps, boilers, cables, all working together in a continuous industrial cycle. From an engineering perspective, the dredge was undeniably sophisticated. But once the larger narrative of smooth technological progress is removed, the meaning of the machine becomes less certain. Instead of a single clear story, several different elements appear at the same time. A powerful industrial device, a demanding mechanical system requiring constant maintenance, a workplace with difficult environmental conditions, a machine capable of reshaping entire landscapes as it moved. All of these descriptions are accurate, yet none of them alone captures the full reality of dredging operations. The dredge becomes harder to place neatly into a single historical category. It was not simply a triumph of engineering, but neither was it a failure of industrial technology. It functioned. It produced gold. It operated in many regions for decades. At the same time, its operation depended on compromises, partial gold recovery, constant mechanical repairs, heavy financial investment, extensive alteration of river valleys. When these elements appear together, the history of the dredge begins to look less like a clean narrative and more like a complex system. A system where engineering, labor, economics, and environment interacted continuously. None of this was hidden from the people who built and operated the machines. Engineers recorded performance data. Companies tracked maintenance costs. Geologists mapped the landscapes left behind by dredging. The information existed. It circulated among specialists. What rarely happened was integrating all of those elements into the public story of the machine. Instead, the dredge often entered history through a more symbolic lens, a giant machine representing industrial progress, an image that fit easily into a broader narrative about modernization and technological advancement. But when that symbolic layer is removed, the dredge begins to look more like what it actually was, a large and complicated piece of industrial infrastructure operating within a very specific historical context, designed to solve a practical problem, built with the engineering knowledge of its time, operated under real constraints, and leaving physical traces in landscapes long after the machines themselves stopped moving. In some regions, the tailing ridges left behind by dredges are still visible today. Long rows of stones crossing floodplains, quiet evidence of machines that once processed thousands of tons of sediment every day. Those ridges are not monuments in the traditional sense. They do not celebrate the machines. They simply remain physical reminders that the history of technology rarely unfolds as neatly as the stories later told about it. And perhaps that is the most interesting part of the dredge's history. Not that the machine existed, not that it was powerful, but that its story became so orderly in retrospect. If for so long we accepted such a clear and structured narrative about a machine capable of reshaping entire rivers, it raises a broader question. How many other technologies from the industrial past are still described through similarly simplified stories? And how many details remain waiting in technical documents, simply because they do not fit as comfortably into the narrative of progress?